Good morning, everyone, and welcome to this virtual herding webinar. Firstly, I'd like to acknowledge the traditional owners of the land on which we work and live and recognise their continuing connection to land, water and culture. We pay respect to elders past, present and emerging. I'm Ray King, and on behalf of Dairy Australia, I manage the virtual herding project. This project is a 4-year project that began in July 2016 to evaluate the application of virtual herding technology across different livestock production systems. The virtual herding project received $2.6 million from the Australian government through their Rural R&D for Profit program. In addition, nearly $1.4 million was provided by a number of rural research and development corporations and also R&D providers. The R&D providers include CSIRO, the University of Sydney, University of New England, the University of Tasmania and the University of Melbourne, and Adjacent Proprietary Limited. And there were additional contributions from Dairy Australia, Meat and Livestock Australia, Australian Wool Innovation and Australian Pork Limited. This webinar will present the main findings from the virtual herding project and the implications for the livestock industries in Australia. The speakers will include Dana Campbell from CSIRO, Megan Verdon from University of Tasmania, Sabrina Lomax from the University of Sydney, Danila Marini from University of New England, and Nikki Reichel and Brendan Cullen from the University of Melbourne. At the end of this each presentation, there'll be a couple of minutes for each presenter to answer questions that you may have submitted. There should be also about 10 to 20 minutes at the end of all the presentations where all speakers will be online to answer your questions. They'll also be joined by Sally Haynes, who's the Chief Scientist at Adjacent. Sally joined Adjacent in 2015 in the very early stages of the establishment of the company and has been instrumental in the development of the commercial East Shepherd product. She manages all their animal trials and has liaised with the project team about this R&D program. I'd like to introduce the first speaker. Dana Campbell completed her PhD at the University of Auckland. She then did postdoctoral work in Canada and US before moving to Australia in 2014 to undertake further postdoctoral research in laying hen behaviour at the University of New England. She then joined the Animal Behaviour and Welfare team at CSIRO in Armidale as a research scientist to begin their work on the virtual herding project. Just a couple of, before Dana starts, can I remind you that if you have specific questions, please click on the Q&A link at the bottom of the screen and type them in. Also, if the box containing the video of the speakers is in the road of the presentation on the slides, you can move it to the side or corner with your mouse. So I just remind people to make sure their audio is off. So Dana, can you start?
Thank you, Ray. I'll just start sharing my screen here. So good morning, and thank you everyone for joining in. So as Ray mentioned, I've been working on this virtual herding program for the last couple of years. I am part of the team at CSIRO, and we have been looking at the application of the technology for beef cattle. And I just wanted to acknowledge that all of this work that I'm presenting today is just a short summary of it. You can find more detailed information in publications online. And the work was a team effort, so I just wanted to acknowledge everyone who was involved in it. So just briefly before I get into the research that we did, I just wanted to give a very short overview of the virtual fencing system just at the level of the animal. So some of you may be familiar with it, but the animals, they do wear devices, neckband devices. They're GPS enabled. So then if you have a paddock set up, you can set a virtual fence line, which creates an inclusion zone where you want the animals to be and an exclusion zone where you do not want them to be. When the animals are in the inclusion zone, they do not receive any types of signals or cues from the devices. As they approach this virtual fence line, the devices will emit an audio warning tone, and this is followed by an electrical pulse if the animal keeps moving forward. If the animals do cross over into the exclusion zone, they will still receive an audio and an electrical pulse as they continue moving further into this zone. However, if the animals turn around to move back in the direction of the inclusion zone, they no longer receive any signals. So this system, it trains the animals to respond to this audio tone alone, and they can avoid receiving the electrical pulse if they stop as soon as they hear that audio. So just an overview of what I will be presenting today. A series of studies that we looked at, firstly to examine the responses of animals to virtual fences if we move them. We then looked at the application of the technology to be able to herd cattle. We then conducted a larger scale study to look at the welfare responses of the animals if we expose them to standard electric fence tape versus a virtual fence, and then the application of the technology to restrict animals from environmentally sensitive areas. So this first study here was designed to look at how the animals respond if we were moving the fences. And this was with the understanding that producers might want to set up temporary fences for the animals, but they would not want them to remember the location of them so that if that fence was deactivated, the animals might still avoid that area. So we had a paddock set up, and the animals were given full access to the entire paddock initially so they could become accustomed to the area. We then set up a single fence line that allowed them to have access to only 40% of the paddock area. And we trained the animals to the virtual fencing signals across a period of about a week. We then shifted this fence line so that they now had access to 60% of the area. We shifted it again so they had access to 80%. And then we thought we'd change it a bit and see how well they really are responding to those signals by switching it to now be lengthways along the paddock. And these here are the GPS plots of the animal movement across that trial period. So you can see that they use the entire paddock area when there is no fence set. They are mostly restricted to this inclusion zone, although there is this initial training period where the animals are crossing over just as they are learning what those signals mean. And then you can see as the fence line moved, the animals responded to it, and they remained within the area that they were allowed to be in, but they were really responsive to this fence line shifting. We see that they had learned that this fence line had moved in just under 4 hours. And the full information of this study is available in an open access publication online. The next study we did was to look at the application of the technology to be able to herd animals over short distances. And so this image here is just a screenshot of the online user interface that you use to communicate with the devices and to set your virtual fence lines. And so these white lines here, there are a whole series of different fences that we were able to activate based on where the animals were in the paddock. And so we tried multiple different types of fence designs, and we had several groups of animals. They all followed roughly the same protocol. So on the first day, we put the animals in the paddock and we had their devices on, but they were set to just have GPS tracking, so no fence line was set. The animals became accustomed to the paddock. And then on days 3 and 4, we had what we call this training fence activated. So this is to get the animals used to the cues. We did not want to be exposing them to moving fence lines and trying to shift them if they were not yet familiar with the signals of the system. We then took the animals out of this paddock on day 5, and then on day 6, we herded them one way down the paddock, and on day 7 in the opposite direction. As I said, we had a series of different types of fences that we tried out to see what might be most successful in moving the animals. And we found that the fence that was most successful was just this back fence. So as the animals moved down the paddock, we activated a fence behind them. And we shifted this as the animals kept moving down. And so this fence was designed to prevent the animals from being able to turn back. So it did not push them. There were no signals provided as long as the animals were moving in the direction that we wanted them to. But if they were to turn around and try and move back up the paddock, then they would hit this virtual fence line and get signals. And these here are just a couple of plots showing the movement of the animals down the paddock. So this is a plot of longitude across time. And you can see that the animals mostly stick together as a group. And this happened within a relatively short period of time. And we found it to, there were no visible stress signals in the animals. But it did very much depend on the movement of them. So you can imagine if the animals were walking quite fast, then it might go quicker. If the animals were moving down slowly, then it would take an extended period of time. And the third study that we did was to really understand whether this new technology, this virtual fencing, might have any type of welfare impact on the animals when you compare it with electric fencing, that physical electric fencing that is used widely. So we used electric tape fencing versus virtual fence. And we had 8 different groups of animals, in which half were in a paddock with electric tape, and then half were in a paddock with just virtual fence. And we did this across 2 cohorts so that there was always a paddock in between the animals so that they were not attracted to each other or influenced by another group. So we ran the first cohort early last year for 4 weeks, and then the second cohort of animals following after. And we took a range of different measurements that were consistent for each group. So on the first day, we put the animals in the paddock. They had their devices on, which enabled us to GPS track where they went within the paddock. We also had ice cube devices on their legs, and these are commercially available devices that automatically record the behavioral profiles of the animals, such as whether they're lying, walking, standing. And then we took initial body weight movement, or body weight measures. And then after they had a week to acclimate to the paddock, we took our baseline fecal samples, and this is to look at stress hormone metabolites within the feces. And then we took another measure of body weight. And so we had this GPS was tracking throughout the entire experimental period, and so were the ice cubes tracking the behaviors of the animals. We then activated a virtual fence or placed the electric tape in. And we gave them a 6-hectare inclusion zone. And we kept this up for the rest of the trial period, and we took weekly fecal samples from individual animals and weekly measures of body weight. And then at the conclusion of the trial, the animals were moved from those paddocks, and then we repeated the whole process over again with the second cohort. And just briefly, here are some of the results that we found. So this first graph here is demonstrating the proportion of time that the animals spend standing or lying. And we have here on the top, these are the animals that were exposed to the electric tape. And on the bottom, the animals that were exposed to the virtual fence. You see these are behavioral profiles across the trial weeks, and then we have cohort 1 and cohort 2. And what you can see here is that there was variation across the weeks of the trial, and variation in how the different cohorts of animals behaved, but there was no major difference between the animals that were exposed to electric tape or the virtual fence. We did find that the animals exposed to the virtual fence exhibited slightly lower lying time. So it was statistically significant, but it equated to less than about 20 minutes per day. So if they're lying for an average around 12 hours, then the virtual fence animals were lying for about 20 minutes less on average. So we're unsure if that might have any other implications longer term, or whether that 20 minutes is biologically relevant to the animals or not. And then this graph here is displaying the fecal cortisol metabolites. So these are the stress hormone metabolites that we collected within the fecal samples. And on top, you have the animals that are exposed to the electric tape, and on the bottom, the animals are exposed to the virtual fence. And this is across the different weeks of the trial. And you can see here that there are very few differences between the animals with the tape or the virtual fence, but we do see clear differences across the trial period. And this matched with the behavior of the animals as well, in that we had got them in from a commercial supplier and they were not well handled. So at the time, you could see that they were quite flighty and avoided people, but they habituated or adapted across the trial period. So these stress hormone measures reflect that. We can see that there are very few differences based on the type of fence that they were exposed to. So from this, we conclude, based on the measures that we took, that there were minimal differences between this electric tape fencing and virtual fencing in terms of behavior and welfare measures. And the full write-up of this study is available in an open access publication online. And so the final studies we did were to look at the application of the technology to exclude animals from environmentally sensitive areas. And so this is very appealing if you've got areas that are not easily able to be fenced, or areas where you just might want to install a temporary fence. And so the first trial was a commercial riparian zone. So this was done on a commercial farm in New South Wales. And this map here, the black area is all the area that the animals had access to when there were no fences set. And then we set a virtual fence line here, the orange dash line. And this yellow is just indicating the area that the animals had access to when the virtual fence line was set. We had to exclude this corner as well, just because it was a tricky corner in which to activate a fence on. So we just had electric tape there at the time. And these here are the GPS plots of the movement of the animal. So you can see when there is no virtual fence that the animals would cross over the river, which was located around here, and access all this area across the river. They were restricted when we had this virtual fence activated, and it was for a period of approximately 10 days. There was a one point where 4 animals did cross over. They crossed over for about 30 minutes before the technology was able to turn them around and herd them back to their herd mates. And then you can see when the virtual fence is deactivated that the animals crossed over, and they actually accessed more of the area than they did before. And this was very rapid as well. So they crossed over within a couple of hours of that fence being deactivated. And the full details of this are also available in open access online. And then finally, we looked at the ability of the technology to exclude animals from an area of saplings that were regenerating. And so this was a trial that was conducted down in South Australia. And this here is a map of the paddock. And we used because we were wanting to activate this red line here, which is a contoured rather than just a straight virtual fence line, which you would have seen in all the other studies I presented. We wanted a more contoured line that followed around the area of saplings. So we activated a series of training fences that gradually approximated this contoured line. And these here are the GPS plots of the animal movement. So you can see that they are remaining within the inclusion zone for the majority of the time. Here you will see that there is quite a bit of blue with animals crossing over. So this was attributed to 3 animals of the group of 20 that had some malfunctions within their device with the versions of the prototypes that we were using at the time. But you can see that across this, and it was a 44-day period that we had these virtual fences activated, and the animals were excluded from the area of saplings for the majority of the time. And this is also available online for anyone who wants to read further about that study. So just in summary, what we know is that the technology, it works across many different situations, but of course there are more applications that we can try to really understand where the technology can be applied. We have not found major welfare impacts at this point based on the measures that we have used. We recommend keeping it simple for the animals. That is because you've got an individual animal learning, but you also have the impacts of the herd as well. So there are social impacts on the way they learn. And so you just need to remember that when you are implementing fences, that it is a combination of both the individual and the social group. And with that, I would be happy to answer questions that there might be.
Thanks, Dana. I'm checking the question box and there doesn't seem to be any yet. I encourage people to use that to ask questions. I have one, Dana. Would you expect a large herd to be easier or harder to move the herd down a paddock rather than a small group of cattle that you had in your studies, or would it matter?
I think it's possibly more about the size of the paddock than just the size of the herd. So we conducted that herding study a couple of years ago using prototype devices, and obviously the technology is changing all the time as they update it. So issues that we encountered then, we probably would not encounter now with updated devices. I think that there is an application to be able to herd them in that same way across larger distances, maybe over extended periods of time. So something similar to mustering. We may be able to herd them short distances, but we would need to try that with updated versions of the devices.
Thanks, Dana. There's a few questions that have come up very quickly. From Philip, is there a control measure for the stress levels of cattle?
So is that in relation to the study that we did where we compared the electric tape versus
I would think so, yeah.
Virtual fence? Yeah, so we did not have any paddocks where there were animals with no fences. But we did take samples from them, obviously before all the fences were activated. But no, there was no control in the sense that we had paddocks where there were no fences activated at all. No, we did not have that.
Thanks, Dana. Another one from, this is from Emily. Is there a minimum space per animal required for the inclusion zone?
As far as I know, there's we haven't looked into that, or I don't think, unless Atchison has developed regulations themselves, because they do have a nice guideline of how producers might implement the fence, and based on studies that they have done as well and their experiences. So I don't know if they have a minimum space requirement that they have listed, but I imagine that this would, vary depending on the farm and the producer and the situation. But at the moment, we have not set something ourselves.
Okay, Dana, there's quite a few questions that you could answer after your presentation, but one final one. Do animals without the device react to the device on other animals?
So we have not, in cattle, we have not tried putting devices on some and devices not on others. But Danila Marini has done that with sheep. And she'll be giving her presentation later. We do have a publication that is just about to come out online showing that animals will respond to the responses of others, but they still have their own devices on. If you mean, does the animal, say, hear the audio of the other device and respond to that? No, not that we've seen. The tone is designed to be at a level that's really just for that animal to hear. I mean, if they're in very close proximity and calm conditions, then they might possibly hear the audio of another animal. But no, it's the audio tone itself is really designed just so that that animal wearing the device hears it.
All right, thanks very much, Dana, for that presentation. It's fantastic.
Thank you.
The second presenter is Megan Burden from the University of Tasmania. Now, after she initially did a science degree, Megan completed a postgraduate diploma in animal science and management at the Animal Welfare Science Centre at the University of Melbourne. Megan then completed a PhD in sow behaviour in 2015 before joining the Dairy Centre at the Tasmanian Institute of Agriculture as a research fellow in the virtual herding project. You right, ready to go, Megan?
Yes, should do. Thank you, Ray. Just share my screen here. Okay. Good morning, everyone. Thanks, Ray, and thank you all for being here. Today, I'm going to talk about the virtual herding research that we have been conducting in Tasmania. And the focus of our research has been on the application of the virtual herding technology in intensive grazing systems.
Excuse me, Megan, I'm only seeing a slide that I don't see the full slide across the whole screen.
Okay. Does it look like a cover slide there that you see?
It's
Megan, you're sharing presenter mode rather than the presentation.
Right, sorry. Let me see. Sorry, bear with me a sec. So I shouldn't be sharing anything now, is that right? And then share screen. Let me see.
yeah, that looks good. Just
That's working?
No.
Just
not
go
there.
to the display settings up the top there, Megan. Display settings.
Yep.
Click on that and then just
Swap that.
Yeah, there you go.
That's working now?
It will do, yeah.
Okay, sorry. Okay,
Just
so
click,
yes.
click the button, sorry.
Beg your pardon?
It's just frozen. Just click the swap presenter view button if you can.
Now it's gone back.
Oh, okay. It wasn't doing anything before, but
Tell me if you see this. Did that change slides then? On your view?
I'm not seeing anything. Are you, Ray?
No, what you had on before was
So, sorry, Megan, the easiest thing to do would be when you click the share screen button on Zoom,
Yes.
you have options of different desktops. You'll have two PowerPoint options. Choose the PowerPoint option that has the actual slide rather than, so when you start the presentation and you go to share screen, yeah, perfect.
very good.
Okay,
Thanks,
third
Megan.
time. Sorry. So that's working.
Yep.
Okay, so now I'll talk to you about the research we've been conducting in Tasmania, which the focus of was the application of the virtual herding technology in intensive grazing systems. And particularly we were interested in answering questions relating to whether the technology can manage cattle off a fresh strip of pasture, and if so, can it be used to improve productivity through a better control of grazing? So our research program was conducted in two parts. And the first part examined some factors that may affect the response of dairy cattle to virtual herding, while the second part looked at virtual herding to intensively manage a grazing cattle. And this part comprised of experiments that simulated grazing regimes that may be possible with the virtual herding technology. And it also conducted experiments that assess the application of the eShepherd prototype. So first, I will briefly summarise the findings from our experiments on the factors affecting the response of dairy cattle to a virtual fence. These experiments used a manual training collar, which was pretty much a moo monitor casing that had been fitted with electronic dog training technology. So this audio and electrical stimuli from these training collars was manually delivered through a control that was operated by a researcher. And our experiments using these training collars showed that heifers with previous experience with an electric fence learnt the association between the audio and the electrical stimuli more quickly than those that didn't. We also found that older heifers learnt more quickly than younger heifers, and more reactive sort of temperamented heifers responded better to the virtual fencing technology. Now, our simulated virtual fencing experiments used temporary electric fences that we manually shifted to simulate grazing regimes that may become possible with the virtual herding technology. In our first simulated experiment, we had 81 pregnant heifers and we studied them for 56 days. The heifers were split into 2 groups and they grazed the same paddock that was divided lengthways using electric fencing. And we applied 2 treatments to the groups. So bear with me while I get my laser pointer on. Okay, so our control treatment is demonstrated up here. And these heifers were provided fresh pasture twice a week. Our experimental treatment, which is demonstrated down here, were provided fresh pasture every day. Our second simulated experiment also looked at increasing the frequency of a pasture allocation, but with lactating dairy cows. So in this experiment, we had 60 mid-lactation cows and we studied them for 28 days. Like the heifers, they were split into 2 groups and they grazed the same paddock, which was divided using electric fencing, and we applied 2 treatments again. So our control treatment, you can see over here in the far paddock with the red fence up here, they were provided fresh pasture twice a day as they exited the dairy. Now, experimental treatment, which is this group here with the yellow line, they were provided the same amount of pasture, but much more frequently, so 7 times per day in smaller strips. And what we found was a more intensive grazing regime increased the live weight gain in the dairy heifers, but allocating pasture 7 times per day reduced milk production by 1 litre in the lactating cows. So there may be a use for virtual fencing to intensify grazing of heifers, say on a runoff block, but the very intensive grazing regime, like the one that we used in our experiment, is probably not the best use for this technology. Our final group of experiments applied the Adjuson's E-Shepherd prototype, which is pictured here. So the first intensive grazing experiment we did using the prototype assessed a single virtual front fence in early lactation dairy cows. And we intentionally kept the design of this experiment very simple because the technology hadn't been applied in this way before. We had 30 cows managed as a single mob, and they were provided a 24-hour allocation of pasture in a new paddock each day. The design of the paddock, which is shown here, was pretty much constant throughout the experiment. So the perimeter fences are these black lines, they were electric fencing, and we imposed a single simple front fence between 80 and 120 metres. The mob of cows were first grazed with this design for 10 days with an electric fence. They then underwent 3 days of training to the virtual fence technology before being grazed for 10 days with a virtual fence here. Behaviour was recorded for a smaller subset of the cows over 3 days in the electric and the virtual fence periods. We also obtained milk samples that were analysed for cortisol concentrations at some points throughout the experiment, and we had daily records of a GPS location, milk production, and pasture utilisation. Now, overall, we found that the technology worked quite well at keeping cows off fresh pasture and contained within our desired inclusion zone area. So on average per day, a cow would spend less than 0.4% of her time over the virtual fence in the exclusion zone, so this zone here. And this is demonstrated by this photograph where you can see the pasture is grazed down up to the virtual fence line, in our inclusion zone. So this is the area we wanted them to stay in. And you've got the fresh pasture over the other side of the fence. That's also shown by this video here, where I'd like you to note that the cows are moving up to the virtual fence line. They're receiving stimuli and they're turning away, but they're continuing to graze. So this is a desirable behavioural response. The GPS records we had show a pretty even spatial distribution of cows across the paddock over a 24-hour period. So here, this EZ here, this is where the virtual fence is imposed. And then as we go along, we're looking at distance away from the virtual fence until you get to zone 20. That's as far as you could get from the fence in this paddock. And if you look at these grey lines, this is how the cows were using their space in that paddock. And it was fairly even over that 24-hour period. However, we did see a reduction in pasture utilisation with the virtual compared to an electric fence, and also a reduction in time spent grazing. But this did not result in a change in milk production. And this may be because that the pasture they were grazing during the period with the virtual fence was more energy rich than the pasture during the electric fence period. There was also some evidence of increased cortisol at day 5 with the virtual fence. And we can't be too sure what the implications of this is, because the animals could be within a normal adjustment period at day 5, and it could also be just a part of a random variation, like this peak we saw at day 6 with the electric fence. So really we need a longer study period to understand what this data means. A final experiment used the E-Shepherd prototype to cell graze Angus heifers. For this experiment, we had 40 heifers, and they were split into 4 groups of 10. 2 of these groups were grazed with an electric front and back fence, and the other 2 groups were grazed with a virtual front and back fence. Now this figure just visually demonstrates our experimental setup. So we've got virtual fence group 1 here, virtual fence group 2 here, electric fence group 1 here, and electric fence group 2 here. You can see that the heifers grazed in adjacent lanes that were separated by electric fencing, which is those thick black lines. Now the groups were shifted to a new allocation every 3 days, and we studied them for 3 pasture allocations. So a total observation period of 9 days. This just shows this is their first allocation, so days 1 to 3, allocation 2, days 4 to 6, and their third allocation, days 7 to 9. And you will note that over the days, the middle 2 groups here moved further along the lanes than the outside groups of heifers. And this is because there was more pasture available in those outside lanes, so less total area was required to make sure that animals had the same amount of pasture for those 3 days. We didn't see any differences between the electric fence and the virtual fence animals in how much pasture they consumed or their weight changes over the experimental period. Now this chart shows the stimuli delivered to the heifers in the virtual fencing groups. So on the left here, we've got audio, and here we've got the electric pulses on the right. And you can see the 2 groups here, so virtual fence group 1 and group 2, group 1 and group 2. Now this top panel refers to the stimuli delivered in their first 3-day allocation. The middle panel is their second, and that final panel there, that's their third allocation. And then within each allocations, the days 1, 2 and 3 are shown by the different colours. What you can see is that the heifers in this first virtual fencing group interacted with the fence and received more stimuli during the second and third allocations compared to heifers in the second virtual fencing group. And if you look at the electric pulses, then the difference is quite clear. Now, if I just remind you of this slide, during allocations 2 and 3, the group of heifers in this first group lost tactile contact over the fence, but still had visual contact with the group of heifers in their adjacent lanes. This is this group here. And this could have been acting as a social motivator, encouraging the heifers to interact with the fence more than they may otherwise have done. So in summary, a single virtual front fence successfully managed dairy cows off fresh pasture, but we did see some reduced pasture utilisation and some indications of increased stress or disrupted behavioural time budgets from day 4 with the virtual fence. We had some success cell grazing Angus heifers with the virtual fence. One group often grazed outside of their cell, especially when they had visual contact with other cattle, whereas the second group were well maintained within their cell. But in either case, a longer study period is really required to fully understand the application of virtual herding technology in intensive grazing systems. Thank you, and sorry for my technical failures. There's a list of papers there that we've submitted or that have been published on our research.
Thank you, Megan. While the questions are coming up, I've got one. Was the less success that you had with the Angus heifer study more a reflection of their limited experience with strip or techno grazing compared to dairy cows that sort of grow up with strip grazing systems?
Yeah, so when we bought these animals from off the farm as well, but we did graze them for 1 month leading up to the start of the experiment as a cell. We cell grazed them, but we did it as a mob of 40. So they actually formed quite a strong social network. And we had a 3-day period to try and get them used to being in different groups as a cell, but I think it was still just a bit too strong, their relationships with each other.
Okay, thanks, Megan. Are there any questions for Megan? If they come up after a presentation, then I'm sure Megan can address them after a presentation. Thanks, Megan. The next speaker is Sabrina Lomax. Sabrina graduated from the University of Sydney in 2006 and then enrolled in the PhD program at the University of Sydney and completed this in 2011 after various postdoctoral studies in livestock at the University of Sydney. She transferred to the Dairy Science Group at the University of Sydney, Camden at the beginning of 2017 as a research fellow to focus on the virtual herding project. So I'll hand over to you, Sabrina, but just before then, if I can remind people to put their questions through that link at the bottom of the page. Thanks, Sabrina.
Thank you, Ray. Hi, everyone. I'm going to give you a very brief overview of the work that we've done for Subprogram 3, looking at the best sub-herd and individual animal management for dairy and beef systems. I have to give most of the credit for all of this work to our PhD student, Patricia, who has really driven this whole project on the ground. She's been the one working with the cows and knows them personally. So all the credit, most of the credit to her, and also Associate Professor Cameron Clark, who is leading the program. So we really focused on dairy cows because Syro has done a great job covering off in the beef space, and we've got a very accessible dairy herd here. But a lot of the results could be extrapolated, although there are a lot differences in the behavior profiles of dairy and beef cows. Our first question was to understand how dairy cows learn a virtual fence. And this would really inform training protocols around how we would best train them to make sure that all animals within the herd learn the virtual fence. So our first experiment looked at comparing training of dairy cows as individuals versus training them in small groups of 6 cows. So you can see a bit of a summary of how we ran the experiment here. We used 24 dry Holstein Friesian cows that had no previous experience with virtual fence. And we tested them either as individuals or as groups at the first stage of the study for about a week. We did 4 tests with the virtual fence that ran for about 10 minutes for each test. After 4 tests, we then crossed them over into the alternate context, so that individuals were then tested as groups and groups were tested as individuals. And this looked at how they retained learning into the different context. We used a setup, an artificial test setup where we had 3 paddocks that were exactly the same parameters. We set a virtual fence about 30 meters up the paddock, so they had another 70 meters before a feeder tracked in at the end of loosened cubes. The idea was that the cows would, within the 10-minute test period, they would walk down to access the feeder tracked in at the end of the paddock and interact with the virtual fence. We measured the amount of times that they interacted with the fence, as well as the stimuli that was delivered by the collars. We did have a few issues with these early stages of the neckbands prototypes, and we lost a bit of data from the stimuli end. So this isn't a comprehensive evaluation of the total number of stimuli, but it shows us some really good trends. What we found was that the number of stimuli reduced between the training and the crossover phases, which meant that animals were learning to respond to the stimuli and respond to the virtual fence. So you can see here at training, the mean stimuli count reduced significantly between training and crossover. And there was no overall difference between individuals and groups across the whole study. Oops. What we did find, though, in terms of interacting with the fence and trying to access the feed, was that cows that were trained as individuals had less or responded better to stimuli when they were moved into groups, which meant that they had learned the association of the stimuli well as individuals. However, cows that were trained in the group appeared to have to kind of relearn the stimuli when they were then tested as individuals. So this means that cows trained as individuals are able to learn the association between stimuli, and it has implications for training. Obviously, we only train them in these 10-minute periods. And training animals as individuals in the long term is not commercially viable. So this informs sort of us building a training protocol that allowed them extra time as individuals and space to interact enough with the fence to learn those stimuli. So then our next experiment looked at implementing a training protocol on pasture. What we did was we set up a 1-hectare paddock and we broke it up into 8 different allocations. For the first 3 days, cows, we had 12 dairy cows, and they had access to the first 3 allocations, which is over allocated based on their maintenance requirements. So there was plenty of pasture, and that meant that they could take their time over the 3 days to learn where the fence was. We then shifted the fence for an additional 3 days so that we could establish whether they had actually learned the stimuli and the cues for where the fence was, or if they just learned the spatial location of that fence. We allowed them an additional 3 days with some fresh pasture in front as an attractant. What we found is that between the 2 grazing allocations, the first 3 days and the second 3 days, there was a significant reduction in the ratio of electrical pulses to audio tones. The ratio is really important because it means that as the ratio reduces, they're responding increasingly to the audio tone alone and not to the electrical pulse, which means that they've made that association. So this was really important to establish learning. However, what we found, as with all studies so far, is that there is a great degree of individual variation in the way that individuals interact with the fence. We had some individuals that would interact a lot with the fence and some that would barely interact at all over the entire period. So this has implications as to how the herd dynamic and the impact of the herd on how cows respond to virtual fence systems. We wanted to then understand if it was feed motivation, how strong feed motivation was as a driver for animals to cross over the virtual fence into the exclusion zone. What we found in our previous study was the fence was actually successful at containing animals for about 99% of the time. So it did successfully contain animals, even though we had cows crossing over the fence line. So we wanted to do a very controlled experiment to evaluate the effect of hunger. What we did is we had two groups of cows, one that was fed a very strict maintenance ration of hay and lucerne cubes, and another group that had ad lib access to as much feed as they wanted to eat. We then used a similar setup where we allowed them to walk down a paddock and reach a feed attractant past a virtual fence. Overall, what we found was that the cows that were fed a maintenance ration were more likely to receive that electrical pulse, so to push through that virtual fence to reach the feed attractant, than cows that had ad lib access to feed. However, this was a very artificial setup, and cows eventually learned that if they just waited, they could leave the test setup and get fed at the end. So you can see that over time, there was very few interactions with the fence in this experiment. So we needed to repeat this on pasture to have a more sort of real life situation of strip grazing dairy cows on pasture. Now, obviously in dairy systems, we have very strict feed allocations, and we need to control pasture allocations for production as well as for our pasture management perspectives. So this study wanted to evaluate if hunger would affect cows remaining behind a virtual fence. And we asked the question, what if we only offered cows the post-graze residual for a day instead of offering a fresh allocation? So the pasture is right at the edge of the virtual fence. This is from training. You can see you get quite a good clear line in the pasture where the virtual fence is set. So we used 10 dry dairy cows for this experiment and a similar setup on the same 1 hectare paddock where we had 10 allocations. On days 1 to 4, we strip grazed them as per normal setup. So we allowed them a fresh allocation every day for the first 4 days. But then on day 5, we held them back on that same post-graze residual. We allowed them 2 days worth of the post-graze residual, and we set up a non-electrified fence tape there to keep them into that area so that they could graze that residual instead of accessing the fresh feed. We measured obviously the stimuli and the amount of time and the location of animals on the other side of the fence. We repeated it again for another 4 days and then held them back on the 10th day again from the fresh feed that was not available to them. In terms of pasture consumption, we allocated them around 2,000 kilograms of dry matter per hectare. And on the days that they were allowed fresh allocations every day, they grazed down to about 1,600 kilograms per hectare, which is pretty standard for a strip grazing scenario. So the average consumption was between 6 and 8 kilos per cow per day of dry matter. On those hold-off days, we only offered them that post-graze residual. And so they obviously had a lot less dry matter to consume. But what we found was that for the most part, they stayed behind the virtual fence. We haven't finished analyzing the location data and the stimuli data, but upon first look, you can see that there was a little bit of a difference between individuals in the number of stimuli, so the amount of interactions with the fence. But overall, the average ratio of stimuli remained the same between the days that they had fresh allocations and the days that they were held off. On the first hold off day, they did interact more, but by the time they came to the second hold off day on day 10, they'd kind of learnt the routine and they stayed behind the fence. So this indicates that you can pretty successfully contain dairy cows with a virtual fence in a strip grazing scenario. But it's very important to look at what the implications are for the individuals in terms of stimuli received. These are just some GPS maps that we've pulled from the data, or rather Pat's pulled from the data. And you can see on the days, this is the day that they've had a fresh allocation, they're grazed much closer together. This is where the virtual fence was. So we do get some animals crossing over, particularly cow 1. She was a cow that received a lot of stimuli and was very curious about what was on the other side of the fence. On the hold off days, they spread out a lot more to graze that post-graze residual. when we look at where the stimuli were delivered, the fence was very obvious based on their GPS locations of stimuli delivery, and all stimuli were delivered within about 10 meters of the virtual fence. So about 90% of the stimuli were delivered within 10 meters from the virtual fence, which was consistent across both the grazing and the holding off days. The fences do vary a little bit between individuals, but overall cows, you know, they were passing across the fence line, but they were returning back into the inclusion zone. So while the hunger is a bit of a motivator, it seems to be that we could successfully contain hungry dairy cows for one day in a post-graze residual. So our last experiment that we conducted was whether social motivations were what kind of effect social motivations had on keeping animals within an inclusion zone. And the question we were asking was whether we could graze two different groups of cows on the same paddock using two different virtual fences. So we trained 24 cows to a 1 hectare paddock. We trained them all in one direction using our training protocol for 3 days. And then we trained them in the other direction using the same protocol, keeping about a 50-meter buffer zone in the middle. For the experiment, what we did is we separated the two groups into 12, and we tried to spread dominance hierarchy between the two groups so it wasn't unbalanced with all the dominant cows in one group and subordinates in another. On the first couple of days, we used, the first day we used a temporary electric fence to keep them on opposite ends of the paddock so they didn't just try and run towards each other. After that, we removed it and used a virtual fence to separate the two groups on opposite ends of the paddock. We moved, every day we moved the fence forward one allocation, and we stopped when the groups sort of mixed and didn't unmix again, which happened on day 5 when the buffer zone was actually around 50 meters. So this is a picture. You can see our two groups of cows looking at each other on opposite ends of the paddock. You can see a pretty nice line in the pasture of where they've been grazing. And I think this was about day 2 or 3. Day 5, when there was around 50 meters between them, 2 cows from each group crossed over and were getting a lot of stimuli. So that was when we ended the experiment. And it appears then that social motivation seems to be a stronger attractant than feed motivation for animals to cross over virtual fence. So there may be some implications there about how we structure subgroups based on their social groups. So overall with our project, we found learning does rely on individuals experiencing those paired stimuli to appropriately learn. And there may be some implications of social facilitation, like as Dana referred to. They've got a publication coming out on that. There is some effect of hunger, but overall we were able to maintain cows behind a virtual fence. And subgroups can be separated on the same paddock, but to a limit. So you have to consider how that buffer zone might affect your pasture utilization. Overall, social motivation seems to be a very strong attractant, and this is definitely an area for further work. Some of the limitations and future work that we found, you know, what happens if an individual can't learn? Obviously, no system is one size fits all, and so there might be some selection pressure on how we choose cows for these systems and not. Social facilitation of learning is really interesting. Someone asked a question about collaring. Do all cows need to wear a collar? Danila will present on her work with sheep. Different fences for different individuals. We found somewhere between a 4 and an 8 meter difference in fences. So that could impact on whether you were trying to have a very strict pasture allocation and your grazing front management. Also, one of the issues that's being addressed, obviously we used very early protocols of this technology, but the time to activate and deactivate fences is something to consider in really intensive strict grazing scenarios. And obviously we'd like to continue looking at work on herding groups of cows for both AMS and CMS systems in dairy. Thanks for your time. And if you have any questions, probably email Pat, but you're welcome to email me too. I'd be happy to answer any questions.
Thanks, Sabrina. I noticed quite a number of questions are coming through, but Dana and Megan and Sally Haynes have been addressing those questions, and Sally Haynes from Adjacents certainly offers a response to some of the more commercial. So please feel free to keep asking questions, because previous presenters will respond, and Sabrina will also respond. She goes through the questions as well. I don't see any open questions at the moment, but before you go, Sabrina, a couple of questions. I know you've looked at a little bit about how animals respond to their mates next door, and I'm just wondering if an animal responds to an audio tone and the electric pulse, then what happens to the other animals that are close to that animal that responds?
Yeah, this is definitely something. Ooh, sorry, that's echoing, right? This is definitely something that we've noticed. We haven't empirically measured that though, and that's something that we're pulling out of the existing data. We did notice that in a very confined area, so when you're intensively grazing animals, they do seem to respond to the audio tones or the behavior of their conspecifics in the same paddock. Now that can be used as a tool for social facilitation of learning. We know that dairy cows particularly learn very well from the others in their herd. So that could be a tool for training. And it could be something that we use if potentially down the track you don't want to put a neckband on every animal in the herd, but it's definitely something we need to look further into.
Just another one from me, Sabrina, before you go. Based on your experience with the separation study, do you think it's possible in a herd to allow one group of cows access to a greater area or a less area of grazing each day compared to the rest of the herd?
I think, it depends. Like right now, the social attraction just of a small group seem to be quite strong. So it depends on how established your social groups are. And it could work if you were grazing, say, different age groups potentially. But again, that needs to be investigated. Cows are very curious and they're incredibly gregarious. So they really rely on sort of group members for cues and learning, but also they're very interested in cows on the other side of a fence. So I think there could be some implications if you were trying to avoid mixing. You could have some implications there. So I wouldn't make a recommendation on that until we were able to experimentally sort of investigate that.
All right, thanks, Sabrina. And I encourage people to ask questions, continue to ask questions. And as I say, the presenters will look at those questions and provide answers. The next speaker is Danila Marini. Danila completed a Bachelor of Science at the University of Adelaide. After graduating there, Danila moved to Armidale in New South Wales in 2013 and undertook PhD studies in sheep and cattle at the University of New England. In December 2016, Danila began her postdoctoral research at the University of New England in conjunction with CSIRO as part of this virtual herding project. So Danila, it's over to you.
Thank you, Ray. Let's see if it's... Let me know if that's sharing the right one.
Yep, that looks all right.
Fantastic. Cool. So yeah, I'll be talking about the virtual herding technology that we currently use to manage sheep. So in the work that I've done, we had to start from scratch with sheep. So we currently use the manual technology. So this is a dog training collar that allows us to apply an audio cue and an electrical pulse in the exact same way that the Adjuson's neckbands work for cattle. And when we've been working with sheep, we've also been using a similar algorithm that allows us to incorporate the sheep's behavior as they're encountering the virtual fence. So what we found is in early research is that we can sufficiently control sheep using virtual fencing in the same way that we can control the cattle. And something that we've had to look at is individual variation and group dynamics and how that affects the use of virtual fencing technology, especially for sheep and merinos, which flock quite closely and graze closely together. And this was something that was brought up in the other presentations as well for the cattle. So we've seen that there's a lot of individual variation, and it's quite important in how this impacts the effectiveness of the virtual fence. So this question was asked about the cattle and how interactions with the virtual fence affects other group members. So this was a group study where we were looking at collective movement and flock interactions. So this small group of sheep is approaching a virtual fence, and this one here received the audio cue and turned around. And what was interesting is, as you'll see, as she moves away, she slowly collects more and more of the flock. So none of the other animals interacted with the virtual fence, but they were turned around by this one sheep, except for this one over here is its own little independent leader. So seeing that kind of behavior with virtual fencing and sheep was particularly interesting, as of course flocks in Australia are much larger than the small flocks we were using. So it would be interesting to know if there's a proportion of the flock that you could have exposed to the virtual fence and still keep it working effectively. So we tested this in Waikerie, would have been 2 or 3 years ago now. So we had 4 paddocks and 4 treatment groups. So the paddocks were set up where we had a control group. So this is 9 sheep that had no virtual fence and GPS tracked in this paddock for 2 days. And at the same time, we tested 100% with the virtual fence. So this is 9 sheep with the virtual fence in place. And then on the following days, we tested a 33% group. So that's 3 out of the 9 animals were exposed to the virtual fence. And then we had a 66% group. So that is 6 out of the 9 animals were exposed to the virtual fence. So we GPS tracked and behavioral monitored these animals for their reaction to the virtual fence, as well as their general behavior. So time spent grazing and lying and all of that. So this red line here is our virtual fence line, and these are the paddocks that were in the previous slide. So this is showing the GPS location that we monitored of these sheep over the 2 days. So the darker the squares, the more time the sheep spent in that location. So what we can see here is that, as expected with our other studies, the 100% virtual fence was highly effective at keeping animals behind the line. Our control animals used a majority of the paddocks, spent a lot of time down here. And of course, our 33% we found was not effective at keeping the flock of 9 sheep behind the virtual fence. What we found really interesting was that with the 66%, it was very effective. So having 6 sheep out of the 9 with the virtual fence was effective enough to keep the entire flock behind the line. So we did see some of the animals here that didn't have the virtual fence implemented did cross over the line for a short period, but as no animals followed them, they quickly turned back to join their flock mates. And that's basically what was reflected with the 33% group, but the other way around. So we had the animals without the virtual fence just went forward across the virtual fence line, and the 3 animals with the virtual fence were highly motivated to stay with their flock. So I just realized, let's get a laser pointer going. So yeah, that was interesting to see the proportions, and like mentioned with the cattle, that social motivation is very strong in whether the virtual fence works or not. So what we have found over the studies that we've conducted where we compared individual learning, so this is training animals on their own, and group training, so that's the previous video that I showed where the group was trained in a paddock together. So we found that when animals are trained alone, they have a very high percentage of receiving an electrical stimulus following the audio cue. And they do have the ability to learn. So in this second study here, this was using crossbreds. They have learnt to respond to the virtual fencing cues, whereas the merinos seem to be quite sensitive to the audio, and so had a low percentage here, and we didn't find much difference after learning. And there was a large variation between the individuals. Now, what's most interesting is when we group train our animals, we find that they have a very low percentage of receiving the electrical stimulus when they're first exposed to the virtual fence. This is through the sensitivity to the audio cue in the first round, and then also them reacting to fellow flock mates and then reacting to their audio cue alone after. But they still have a learning curve, so these animals in a group still learn and even further reduce the electrical stimulus received when interacting with the fence. So they're reacting to the audio cue alone, which is important. We've also looked at a short-term study of improving pasture utilization for virtual fencing. So we basically wanted to see if we could graze sheep in a small section, so mimicking the strip grazing for your cattle or even techno grazing. So we have this really small area of 8 by 8, and the sheep were in here for about 4 hours a day and then moved on to the next one the next day. So it's a very small paddock. We have 6 sheep in here, and we also compared this to an electric fence group. So we wanted to see if virtual fencing was comparable in grazing and didn't affect the grazing and behavior of the animals as well. So there's a lot of fences in this. Because it's 8 by 8, we only implemented the virtual fence in front of the animals. So then they didn't have confusion in going back. And the setup for the electric fence group was exactly the same. So they had these permanent fencing behind them and on the sides, and then they had the electric fence at the front. So here we have is our virtual fence at the front with the yellow tape there. So what we found was that the grazing for the virtual fence and the electric fence group was exactly the same. So in the time that the animals spent in these paddocks and grazed, they ate the same amount, which is really good. So we found that the virtual fence had no impact in the sheep's behavior and their grazing behavior. And we also found, interestingly, we measured the pasture at the fence line, and we found grazing at the virtual fence line and the electric fence line was exactly the same as well. So sheep exposed to the virtual fence for these intensive grazing situations still graze the pasture uniformly, much like the electric fence group. Excuse me. So something that's been important for virtual fencing with sheep is also looking at the welfare assessment. So this has been done with our PhD student, Talisa, where she looked at the detailed welfare assessment. So I mentioned earlier that the sheep, especially merinos, were very likely to react to the audio cue without having ever experienced virtual fencing stimuli previously. So we wanted to make sure that the audio cue as well as the electric stimulus that we were using was not overly stressful to the animals. So to do this, we compared our electrical stimulus, which is this group here, ES, with a beep, which is the one we use for the virtual fencing collars. And then with a dog bark. So this is something most sheep will encounter in their husbandry procedures and throughout their life on farm. and then a typical restraint procedure. So this was basically tipping sheep, so as you might do for shearing. And then, of course, we had a control group of animals which had no exposure to any treatment. So what you're seeing here is a graph of the cortisol, so the stress hormone that we measured before treatment at 0, and then at following time points after treatment. So up here is the plasma cortisol level, and then across the bottom here we have the time in minutes. And what we found in terms of cortisol response was that there was no difference between the beep that we use, the electrical stimulus, and dog barks, and the control. So that's having no treatment. And we found that the restraint, which has been shown before, is a lot more stressful of a husbandry procedure. So this is indicating that exposure to the virtual fence is no more stressful than something that sheep would encounter as part of their normal yearly husbandry procedures. We also looked at behaviour, and with behaviour responses, so such as avoidance behaviours and some negative and then some positive behaviours such as exploring. We listed the least to most aversive treatments. So for this, it was the control, so no treatment, the audio cue of the virtual fence, then a barking dog, then our electrical stimulus, and then of course restraint. So this is using the virtual fencing stimulus out of context. So it would be similar to when they first ever encounter those stimuli in a paddock. The next welfare assessment was a little bit more detailed and complicated, I guess. So what we were basically looking at is, I guess that the efficacy side of virtual fencing. So something that's very important for virtual fencing and in terms of the welfare of animals is whether it is predictable and controllable. So having virtual fencing take into account the animal's behavior, so that is they turn around when they hear the audio cue, and then also having that warning system, so the predictability of the virtual fence coming up is very important for this to be welfare friendly, and we found it's a very good way for them to learn. So to compare this learning of the virtual fencing system, so having that predictability and controllability, we compared animals who had no training and walking down a laneway. We had our positive punishment, which is our normal virtual fence training. So that is, they hear the audio cue. If they turn around, they get nothing. If they keep walking, they get the electrical stimulus. So that's involving their behavior. We then had classical conditioning. So this is your standard training. It's often used for dogs, so they get a sound and a reward, but in this case, they get the sound and then they get the electrical stimulus. So this classical conditioning did not take behavior into account. So it doesn't matter what the animal does, they can't change the outcome. We then tested these animals in a laneway. So positive punishment got their audio warning in a laneway saying the virtual fence is coming, but no electrical stimulus. And then our classical conditioned animals received just the audio and the other half received the electrical stimulus. So this is basically the positive punishment is our predictability and controllability that they get in paddock. And these two are uncontrollability basically. So again, we looked at the stress response with cortisol as well as the behavior responses. So again, we have cortisol response up here and the time following treatment. So treatment occurred at 0. And what we found was that our control animals down here and our virtual fencing tested animals, so the positive punishment, which is like the virtual fence in the field, had no difference in their stress response when they encountered the stimuli in the laneway. For our classical conditioning, they had slightly more of a stress response, and then the animals that had the electrical stimulus paired had a significant difference to these control and positive punishment animals. So this basically is just highlighting the importance of the virtual fencing stimuli and how it's applied, and its predictability and controllability on animal welfare. So the outcomes of the sheep studies was we've identified a minimum electrical stimulus that is effective at keeping the sheep behind the virtual fence line, but using those welfare studies, we found that they do not significantly impact the animal's welfare. Associative learning facilitates rapid learning of the virtual fence and highlights the importance of that predictability and controllability of this system. Virtual fencing is very effective when you use it in a group, and the animals learn a lot quicker in this group phase, and yeah, makes the fence highly effective. So where to next for sheep? We require an automated system. So as I mentioned, everything's done manually with these dog collars, and there's potential to either modify the Adjuson's neckband for sheep or looking to the future with something like an ear tag. So thank you.
Thanks, Danila. Again, I encourage people, if they've got questions specific for sheep work, that address them to Danila. We've got a couple through, Danila. From Warren, how hard was it to design a neckband for sheep that delivered the electrical pulse through the fleece?
Yeah, so for our merinos that we've had to use, so we are using dog collars, so we didn't have the opportunity to modify it very much. So that required us to actually clip the sheep's wool every few days, because as you know, merino wool grows very fast and it's a very good insulator for the electrical stimulus. So that's something that we had to overcome as part of our research.
And another one from John, were any crossbred or British breed type sheep used in the program? And I've heard you mention that you did use merino and also crossbred. Can you just comment on any differences in breed or temperament?
Yeah, so we did use crossbreds for this study as well. So one of the earlier experiments that we did. The difference that we found was that they're not as sensitive to the audio cue straight off the bat like the merinos are, but they still learn as quickly as the merinos, and they also are effectively kept behind the virtual fence with the same level of electrical stimulus.
And another one, Danila, from Emily. How many sheep were included in the welfare assessment work you did?
So with the welfare assessment work, we had relatively large groups. So I think, so to make sure that we had statistical significance and all of that. So for one of the studies, I believe the minimum was 16 animals per group, which is sufficient for cortisol and behavioural measures. And then for the more complicated study, we had 20 animals per group.
Thanks, Danila. And there's another question from Marie about any information on setup costs, equipment costs, and how is virtual herding proceeding legally in Victoria. I might leave that to the panel session where Sally Haynes will be available. So again, if you've got specific sheep questions, please put them in the Q&A box, and I'm sure Danila will be able to answer those. Thanks, Danila. The next final presentations will be done by Nikki Reichelt and Brendan Cullen. Nikki completed a graduate and master's degrees to develop her knowledge and skills in social research and environmental studies. Nikki returned to the university sector in 2008 as a research assistant before transferring to the Rural Innovation Research Group in the Faculty of Agriculture at the University of Melbourne in 2015. And she joined the virtual herding program in 2017 and leads the Subprogram 5. Following on directly is Brendan Cullen. Brendan completed a Bachelor of Ag Science degree and a PhD on pasture plant physiology from the University of Melbourne. He is now a senior lecturer in grazing systems in the Faculty of Agricultural Science at university, and has contributed to this virtual herding project by investigating the benefit cost of implementing virtual herding technology on farm. So if I can ask Nikki to begin.
Right, thank you, Ray. Good morning, everyone, and great to be here to present our key findings from Subprogram 5. So our subprogram team includes Brendan Cullen, Ruth Nettle, and myself from the University of Melbourne. And our research focuses on the people side of things. So you've heard all about the animal side. I'm going to be talking about the people side. So the photos in this slide show a small sample of the people that we have engaged, and I'd like to thank all our stakeholders for their thoughtful insights, but I'll talk about our stakeholders a little later. So our subprogram has two main objectives. The first one is to identify the key considerations for adopting virtual herding technology from a range of perspectives. The second objective is to inform the value proposition for adopting virtual herding technology by estimating the economic value from certain applications. And this is ultimately to define an adoption pathway for this technology across Australia's livestock industries in beef, dairy and sheep. So our subprogram has two main methodologies to achieve our objectives. The first methodology is a participatory technology assessment, and I'll be speaking to that first. And this is followed by our second methodology, which is a cost-benefit analysis that Brendan will be presenting. Just to provide you with a broad description of a technology assessment, this is a European-based method, and it's designed to engage a variety of people to make an assessment of a technology to include not only the scientists and the technicians, but also the end users, other stakeholders and general citizens. And this is a way to understand the role of new technologies in wider society and as a means to anticipate any harm from these technologies on our human and non-human communities. So who did we engage with in our virtual herding technology program? So since 2017, we've held a series of focus groups and semi-structured interviews with a range of stakeholders, now totaling 80 people. And these people represent the livestock value chain. So that's from livestock producers to food retail companies, also including agricultural advisors, as well as a food processor. And we also wanted to represent public interests in digitalising agriculture by state government departments and improving Australia's performance in environmental management, represented by regional catchment bodies. So we asked our stakeholders to consider what they thought were the benefits, opportunities, challenges and risks from adopting and implementing virtual herding technology on livestock farms. We also asked them to look at what value they saw for their own sector from this technology by being adopted by Australia's livestock industries. And we also asked them to consider what role they thought that they could play in the adoption space. So out of all of our stakeholder results, we came up with 6 key considerations for adopting virtual herding technology. So the first 3 considerations are focused at the farm scale, and the last 3 considerations are focused beyond the farm gate at a policy and societal scale. So I'll just focus on the first 3 considerations for this presentation mostly. So when we asked our stakeholders what they anticipate for the benefits and opportunities from adopting this technology, a common mix of applications and benefits were mentioned. These include better pasture and fodder crop allocations to maximise the utilisation of their feed base, micromanagement of subherds or individual animals for more precise livestock management, a reduction in labour costs from associated physical fencing, efficient management of different land classes on livestock properties for environmental outcomes and improved pasture condition, as well as being able to monitor and manage their livestock remotely as a social convenience. So being able to shift livestock from your car, your cafe, your neighbour's kitchen, your home office. However, a more fine-grained analysis indicates that there were applications identified by our livestock producers that were particular to northern beef. For example, being able to perform clean musters, or for southern beef, being able to strip graze in high rainfall areas. A specific application for dairy was reduced feet soreness by using flexible laneways, and for sheep, creating smaller mobs during lambing season for easier monitoring. So what do these results mean for adoption? Well, an industry-specific focus for adoption could be attractive to producers, and an offer of a single application will probably not get this technology over the adoption line. It also means that the adoption process should manage people's expectations about this technology, about what it can currently do based on proven applications, as opposed to what is not possible at this point of time. So moving on to the second key consideration, when we asked our stakeholders what they thought were the possible challenges and risks with virtual herding technology, there were 7 main concerns, and I'm not going to talk across all of them. However, I will mention that a key barrier for adoption is not being able to access financial data from any commercial trials to clearly demonstrate a clear return on investment. While another key barrier was having low confidence in Australia's regional infrastructure to support the effective use of this technology that relies on GPS and internet access. So what do these results mean for adoption? Well, an adoption pathway will need to respond to these commonly perceived risks and uncertainties, whether they are real or not, by demonstrating that they can be easily overcome and to strengthen the value proposition of this technology. So moving on to our third key consideration, our stakeholders made it very clear that it will be critical to develop and provide an appropriate and comprehensive support system for the adoption journey, because this technology will be a learning challenge for many producers and adoption support providers. And this learning challenge is in terms of understanding the animal welfare aspects of this technology, understanding how the audio cues and electric pulses are triggered and sequenced, learning how to manage the water points in virtual paddocks when fixed water infrastructure is used, and having the skills to interpret the data outputs from the neckband. So any adoption pathway should include significant user training and upskilling in how to get the most out of this technology. So I'll just briefly mention the other 3 key considerations that I've considered or called them beyond farm. So our stakeholders indicated a general uncertainty around the governance of the data generated by the VHT system. And this is in terms of data accessibility, ownership, security, management, and privacy. And these concerns align with research findings on digitalised agriculture, which reinforces the need to develop big data governance systems that are transparent and empower the farming sector to capitalise on their data assets. Also, most of our stakeholder groups brought up and engaged with the topic of maintaining the social licence of livestock producers using virtual herding technology. So while a large majority of our stakeholders did not express their concerns with the use of audio cues and an electric pulse to manage animal behaviours, they were worried that the general public may view this piece of technology as unethical. And this might be based on misinformation circulated through social media and also being influenced by any animal welfare organisations who deem such technologies as harmful. So an adoption pathway for virtual herding technology should be supported by a public education strategy. We also briefly explored the need for regulating the use of this technology. While there were no unanimous support for regulating the use of virtual technology for natural resource management outcomes, both the food retailing companies identified the need for VHT use to be monitored and audited by independent third parties on farm to verify and protect the integrity of branded products labelled as animal welfare and/or environmentally friendly. So more research needs to be done in this area. However, an adoption pathway should consider the regulatory context of this technology. So moving on to coming up with a recommendation for an adoption pathway for virtual herding technology. The answer is that we don't have a specific adoption pathway as yet, but we are getting close. So our last activity for Subprogram 5 has involved putting together a consultative panel of 13 members who were deemed AgTech and adoption experts from the public, private and industry sectors. So the process has been to put together a discussion paper outlining our social research to date. And we then asked for specific responses to our discussion paper, including asking panel members to sketch out a possible adoption pathway with their rationale. Next week, our panel and our subprogram are discussing and are hopefully reaching some sort of consensus for recommending an adoption pathway for this technology. So I just wanted to give you a glimpse of the panel's thinking so far. So there have been about 8 different suggestions for an adoption approach based on 5 main options represented in this diagram. And it also includes combinations of these different options. So in terms of the green layer, this is called the generic technology transfer approach, and it represents the current situation for adoption. So this adoption pathway features the commercial developer through an authorised distributor and retailer. Technical know-how is the key form of support in this pathway, and it's delivered through an early adoption program targeting North beef producers. The second approach to adopting this technology is a customised service approach that is industry specific. And so this pathway features support from livestock industry bodies who take a lead role in developing adoption support services specific to the beef, dairy and sheep industries. A key feature of this pathway is having a demonstration farm for each industry set up in key production regions, and on-ground support is delivered by agricultural advisors who have been certified to give advice on this technology. So they've had some training, that's what this pathway assumes. And third, the orange layer is the community of practice approach. This pathway features support from building a community of practice around VHT and could involve advisors, AgTech specialists and other stakeholders. The key feature of this adoption pathway is that it is a collective venture as opposed to an individual one-on-one adoption venture. The fourth layer is an adoption pathway that begins with understanding the adoption situation of each producer and production region to provide a targeted and agile adoption approach which acknowledges the diversity in agribusinesses, the biophysical features of sub-regions and markets. Last but not least is the maroon or outer layer, which is approaching VHT as a top-down governance response to manage the technical, ethical and animal risks involved with this technology, as well as encouraging collaborative partnerships for on-ground support. So I don't have a definitive answer for an adoption pathway for virtual herding technology right now, but we hope to have one over the next few weeks. So that ends the presentation on the participatory technology assessment, and I'd like to hand over to Brendan Cullen.
Okay, thanks for that, Nikki. I'll just share my screen with you. So while I'm just getting that up, the cost-benefit analysis approach was, what the approach was to take some of the learnings from the other aspects of the project and think about how that would apply in a whole farm system. So what the applications would be and what the anticipated benefits were. So what we've done in this section is to pick out 3 case studies of well-managed farms, a pasture-based dairy system in West Gippsland, a mixed sheep and beef property in Western Victoria, and an extensive beef production system in Western Queensland. So we considered these to be well managed farms, pretty much at the top of the game. So the question was around, well, what's the additional benefit of implementing virtual herding technology on top of, you know, what they're doing already? So the approach we've taken here is to calculate a break-even cost of the technology. So essentially, it's how much could the farmer or farm manager invest in this technology and make it profitable. So that's the break-even cost. And the reason we used a break-even cost is because the actual costs are commercially sensitive, and so we can direct questions to adjacents about that. But yeah, so the numbers are a break-even cost, or how much can I pay for this technology based on the applications. And another important assumption in here was that we assumed a 5-year lifespan of the technology in these initial analyses. So what I'll do is just take you through each of the case study farms to give you a snapshot of the results. So for our pasture-based dairy farm, the applications are listed down the left-hand side there, and then the break-even costs on the right. So first application was around fetching cows for milking to save on labour and vehicle use. Moving the cows from the paddock to the dairy. We didn't assume all the labour would be taken away, but there was a reduction in labour and vehicle use. And if we implemented that, and that was the only application on the farm, then the break-even cost is $77 per cow. So I could invest up to $77 per cow, and that'd be a profitable investment with a 15% return, as I had on the previous slide. But there's more applications that we could see on this farm. So number 2 was around reduced pugging damage. So this is flexibility in grazing management without fixed fences to allow you to graze areas and soil types which are less susceptible to pugging damage. The third one is quite a sophisticated application, looking at splitting pasture allocation into subgroups of the herd. So early milked cows versus later milked cows, and getting increased milk production from those later milked cows because of preferential allocation of both the quantity and quality of pasture. So if we look at application 3, the break-even cost there is up to $238 per cow. So we're certainly getting in to a realistic range in terms of the break-even cost. And that, when I say realistic, that's based on the costs of other kind of activity meters for animals. We can also think about these as combinations of applications. So here, number 4 combines the fetching application of number 1 and the increased milk production in number 3. And then if we look at both of them in combination, and we couldn't see why we couldn't use that in combination on this farm, we're up over $300 per cow as the break-even cost. So I'll move on and talk about the mixed sheep beef property in Western Victoria. So this, the first application here relates to using the virtual herding technology on outblocks. So there's a home farm, there's 2 outblocks as well, and they pay people to manage the outblocks. And so the first application is reducing labour on those outblocks and getting better control of grazing to increase pasture utilisation on those outblocks. And this did look very promising. With a break-even cost of over $400 per cow. Applications 2, 3 and 4 here relate to use on sheep, and we're adding applications on. So the landscape of this property is quite undulating, and there's uneven distribution of grazing across the farm. So the first application here, application number 2, is using the technology to improve grazing utilisation across the landscape, across that undulating landscape, to improve pasture utilisation and pasture persistence by avoided overgrazing. So $55 per head of sheep was the break-even cost there. Application 3 here, we're adding on improved riparian management without additional capital expenditure on fencing. And you can see the break-even cost. And application 3, or application 4, is the combination of 3 applications. So improved pasture utilisation, riparian management, plus decreasing paddock size and mob size to improve lamb survival of twin lambs. So on this case, we were moving from 140% to 160%. And so you can see with the combination of applications on sheep, we're coming up to just over $100 per head break-even cost. And moving on to the beef farm we looked at was in central Queensland, a relatively short growing season environment here. So applications were partial mustering for branding and weaning. So it wasn't completely eliminating all mustering points, but assuming we'd bring the cattle to a central point, so we wouldn't need a helicopter and reduce labour. So $35 a cow for that, labour and vehicle use reduction. And then we looked at some combinations of improved carrying capacity. So increasing carrying capacity through better spatial and temporal distribution of grazing. And so we're up around $255 per cow. So again, in that realistic range. Applications for increased weaning weight and increasing branding rate from 80 to 85%. This farm was already had very high branding rates, so there wasn't that much potential to increase that here. And so those last 2 applications are around providing access to higher quality pastures. Okay. The assumptions that we use, or the economic outcomes, are quite sensitive to the assumptions used in the analysis. So 2 of the key ones are around the lifespan of the technology. As I said at the start, we assumed 5 years for all the analysis that I've presented. But if the technology lasted 10 years, then the break-even cost would increase. So if it lasts longer, I can afford to pay more of it. If it lasts 10 years, then I could pay 50% more than the prices that I've quoted here. The other thing is around the magnitude of the production benefits that you're going to achieve. So, there's quite a bit of uncertainty around that. So we've done some sensitivity analysis, and just one example of that is for the carrying capacity of that beef property. The baseline assumption I used was a 20% increase, or 80 cows, which gave us that $255 per cow benefit. If the increase was smaller, there'd be less benefit. If the increase was larger, so a 30% increase, that's up to nearly $350 per cow. So, it's going to depend on the farm context. This farm was quite limited in the amount of feed, so that the increase in carrying capacity was small. In other farm contexts, the limitations are going to be different. Okay, so some general findings from this cost-benefit analysis. Across those three properties, we found that the labour savings alone were not enough to achieve realistic break-even costs. So we needed to have a combination of labour savings plus some gains in pasture utilisation or animal production. The results are quite sensitive to the assumptions, and as this is very new technology, we don't know all the answers, so we had to make some assumptions through doing these analyses. The virtual herding technology in sheep production systems doesn't appear to be profitable because of the large number of net bands required. So the assumption we made here was that all the mature sheep had a neckband on it. Some of the research showed that maybe we don't need that. We could still control the animals with only maybe 2/3 of the animals with neckbands on them. So that would change the economics here as well. There are also opportunities for improved environmental outcomes, and they haven't been fully factored into the analysis that I've presented here. And it's very important to realise that the costs and benefits will vary for individual farms. And so the sensitivity analysis starts to highlight what some of those differences are. Okay, so thank you for listening to our results from Subprogram 5, and we'll move on to questions.
Brendan and Nikki, thanks for that. I'll ask all the presenters to come back in, and I'll ask Sally Haynes, just to, because there have been a fair few questions about the commercial use and the regulations involved. I'll ask Sally Haynes to provide an overview of the technology and commercial implementation by the livestock industries. So,
great. Thanks, Ray.
Sally.
And I just wanted to acknowledge the incredible work that the Virtual Herding Group and all the associated organisations have put in over the last several years. And it's been a lot tougher than people probably realise, because they got handed the early prototypes while we continued our development. And so what we're seeing now, has developed and improved extremely rapidly. So it's been really tough on the guys. So thank you so much for sticking with us and supporting the technology. A couple of the big questions that we're being asked, I guess, just around commercialisation. We're currently looking at commercial release in the first quarter of 2021 in Queensland for northern beef. We have scaled up considerably. We have run a 3-month trial on a extensive rangeland property in Queensland. We went from 250 to 450 to over 500 cattle in 2 mobs over quite a large area, sort of 13,000 hectares and another 4,000 hectares in another paddock. And that was really fantastic. And we're currently running a trial on a slightly different property without such large paddocks, but they have real issues with resting paddocks because the soil is not of great quality. So we're working with them to reduce the impact that the cattle have on the pasture and move them sort of every couple of days instead of once every 8 days. So that's where we're at from a commercial perspective. And if you would like any more information about that, please contact Adjacense. I'm all about the animals. I'm not about selling the product, so I'm not here to sell the product. I'm only here to talk about the animals. A couple of other questions that came up. One about social learning. We're definitely seeing that at a large scale. So we do like to take very noted learning metrics when animals are first introduced to the virtual paddocks. And we are certainly seeing certainly differences between animals, but really interesting is when you have half a mob of experienced animals and you add another half, maybe 120 or something, or 200 that are naive, they seem to learn a lot more quickly. So there's definitely something, some social learning happening. And then the last question that came up quite a bit was around regulations. I've also been quite heavily involved in that. It's not easy, as anyone in the industry would understand. And we've been working with a number of state governments on this. And I guess from our perspective, we provide all the evidence that we can, but I guess we need industry. If industry want to adopt it, then that pressure has to come from industry, because we're a business and we can't influence government. So we've worked very closely with all the animal welfare groups and advisory bodies and things, but that push really needs to come from industry. Does that pretty much answer the burning questions for the day?
Okay, thanks, Sally. There's quite a few questions up on the Q&A. I'll go through a few of them, but I'll ask the presenters to type their answers in if we don't get to them. I think this is probably to Brendan. What about looking at cost analysis in the form of access to feed that is not fenced? I think this is related to being able to graze public lands. Would the technology be feasible for that?
Yeah, I think absolutely it would be. So each situation you're going to look at is going to have different constraints associated with it. So that sort of implementing tactical management where it may be a riparian area or public land where you want to be able to graze for a period during the year and not having to invest into the capital infrastructure for physical fences. I think that absolutely is a feasible way to do it.
And another one, Brendan, is the value for cattle in Victoria based only on labour savings or the actual value of improved productivity? I think you mentioned that improved productivity is going to probably be the main driver of the use of the technology.
Yeah, that's right. So in that one mixed farming, it was most of that benefit, around $400 a cow, came from improved pasture utilisation. But the labour saving was fairly substantial, probably about 1/3, 2/3 in that specific example.
And this is probably one for Megan from Lindsay. If animals were trained as calves and used as adults on a daily basis, could we see far less electric pulses being needed and maybe being able to do more complex actions?
Thanks, Lindsay. So we did run an experiment where we introduced the technology to young animals. So these were dairy heifers. They were 6 months, 9 months, or 12 months of age when we trained them. And then we retrained all of them at 22 months of age and compared them to a naive group of heifers that were also trained at 22 months of age. And we actually found that none of them did better than the 22-month-old animals when they were retrained. So that seems to suggest that there is no benefits to introducing them at that young age in terms of trying to get a faster response or a better adjustment when they're older and closer to calving age. But we don't really know how long they can go between having the technology and needing that reinforced in order to retain that knowledge. I don't know if Sally understands any more about that.
I was just going to add to that. We're just recently doing we just recently completed a cow-calf trial in New Zealand. So we actually had unfitted calves with their mothers, and we were actually containing the cows, even though the calves weren't fitted with neckbands. So that was just, we haven't gone less than 6 months at this point. We're looking for a weight, but that was really promising in terms of how we can go from, in a cow-calf operation.
Sally, while you're there, another question, and I think Atchison's see this as a potential as well. It's from Sheila, and she identifies that 2,400 kilometres of fencing have been lost in California due to wildfires or bushfires. How do you see the technology being used in Australia when we do have a lot of bushfires?
Yeah, look, and that's actually something that has been pushed from a number of industries across states, and we've had regulators come to us saying that the push is the bushfires, the floods, the whatever, and certainly there's also areas, so around the looking at the runoff into the Great Barrier Reef, so those riparian areas where you physically cannot fence them. It's just not possible in terms of the terrain, and so I think there's opportunities there for virtual fencing to be of great value, not only to the livestock industry but also to the environment, and particularly if you've got wildlife corridors and you don't want to be cutting wildlife, off from those riparian zones. We've sort of seen the injuries that wildlife get as well. So I think there's multiple options. It's important to remember we have not designed this as a boundary fence only. You do need to have a boundary fence. This is internal fencing, but certainly in those emergency situations, a fence is better than no fence.
Thanks, Sally. One for Brendan, we're getting near the end. In dairy farms, there's been work also looking at collars or neckbands being used for other purposes, like activity monitoring or lameness detection. would that change the economics for dairy if we could incorporate other technology?
Yeah, look, I think it would, absolutely. And all the case study farmers that we talked to recognised the value of this would increase for them if there were other technologies integrated with the virtual herding. So that would be activity monitoring, you know, heat detection, those sorts of technologies. So they all recognise that across all three of those case study farms.
All right, thanks, Brendan. I know people are on timetable, so I'll draw the webinar to a close. Videotaped and will be available on the Dairy Australia website and other websites in about 2 weeks' time, but we'll let you know about that. The project's also preparing a series of technical notes which will discuss potential uses of the technology in the livestock industries, and those technical notes will contain case studies of where we've applied the technology in the livestock industries, and you've heard a bit about it today. And again, these should be available next month sometime, but we'll keep you informed about that. Finally, I'd just like to thank you for attending today, and a special thank you to the members of the project team that presented here today. So with that, we'll finish up, and again, thanks very much for your attendance. Bye.